Have you ever wondered if communication faster than light could be possible? Imagine for a moment a universe where messages zip across galaxies in a blink, where distance is no barrier to instant connectivity. This isn't just idle speculation, it's a question central to our understanding of the universe, and it's rooted in a phenomenon that puzzled even the great Albert Einstein: quantum entanglement. Now, to understand why this question is so compelling, we need to go back in time to the early 20th century, when Einstein revolutionized our understanding of the cosmos. He proposed a theory of relativity that fundamentally altered our perception of space and time. One of the key assertions of this groundbreaking work is that no information-carrying signal can travel faster than the speed of light. It's a cosmic speed limit, if you will, and it applies to all particles, whether they're massive or massless. So, where does quantum entanglement fit into this picture? Well, when particles like photons become entangled, they share a combined quantum state. It's as if an invisible thread links these particles, creating a connection that allows information about one to instantly affect the other, no matter the distance separating them. Experimental evidence backs this up, showing pairs of entangled particles in correlated states that defy classical expectations. But here's where things get tricky. The tantalizing idea of using quantum entanglement for faster-than-light communication hits a stumbling block the moment an observer tries to encode information by forcing an entangled particle into a specific state. The entanglement breaks. The other particle remains unaffected, maintaining a random quantum state. The correlation between the two particles is severed, dashing our hopes of transmitting information. But what if the rules of quantum mechanics were to challenge this fundamental tenet? What if the complex dance of quantum mechanics, where randomness reigns supreme, could somehow circumvent the cosmic speed limit? Is it possible, or is it merely a quantum conundrum, an intellectual exercise that challenges our understanding of the universe? Stay tuned as we delve deeper into this intriguing quantum puzzle. Enter the world of quantum mechanics, where particles can become entangled. This is the realm where the ordinary rules of physics are left behind and a new, more complex dance begins. A dance we call the quantum tango. Consider two particles. Let's call them Romeo and Juliet. These particles interact in such a way that they become entangled, sharing a combined quantum state. This entanglement creates an invisible link, a quantum thread that binds them together. Regardless of the distance between them, be it a few inches or countless light years, a change in Romeo's state will instantaneously reflect in Juliet's, and vice versa. This phenomenon defies our classical understanding of the universe and has fascinated physicists for over a century. But what does this mean for information transfer? On the surface, it seems we've stumbled upon a method for faster-than-light communication, right? You manipulate Romeo's state on Earth, and Juliet's state changes instantly on Mars, conveying the information. It's as if Romeo and Juliet are performing a perfectly synchronized tango across the cosmos. However, this is where the dance becomes intricate. The moment you try to force Romeo into a particular state to encode information, the entanglement breaks. Romeo may continue his dance, but Juliet is no longer in sync. The quantum thread that linked them is severed, and any information that you tried to send is lost. It's as though Juliet decided to freestyle, leaving Romeo to dance alone. This is the crux of the matter. The delicate dance of quantum entanglement allows for instantaneous correlation, but not communication. You can't control the steps of the dance without breaking the rhythm. The inherent randomness in quantum measurements, the unpredictability of the dance, makes it impossible to choreograph a desired outcome. However, the phenomenon of quantum entanglement does not make faster-than-light communication a reality. While the quantum tango is a fascinating dance of the universe, orchestrating it to our tune remains a feat beyond our reach. The quantum world continues its dance, reminding us that some rhythms are best left to the cosmos. While quantum entanglement might seem promising, there is a critical catch. The invisible thread of entanglement that binds particles together in a shared quantum state, allowing for an instantaneous exchange of information, might seem like a golden ticket to faster-than-light communication. However, this tantalizing prospect is thwarted by a fundamental obstacle rooted in the very principles of quantum mechanics. Imagine yourself as a quantum physicist attempting to use entanglement for communication. You'd want to encode a message into an entangled particle and hope that its partner, potentially light years away, would instantly reflect that information. Here lies the conundrum. The moment you try to force the particle into a specific state to encode your message, the entanglement breaks. It's like trying to thread a needle with a rope. The task is simply incompatible with the tool at hand. This disruption leaves the distant particle unaffected and blissfully ignorant of your attempted meddling. It continues to exist in a random quantum state, oblivious to your encoded message. The once entangled duo is no longer in sync, severing the correlation between them and spelling disaster for your communication attempt. At the heart of this quantum quandary is a distinction between making a measurement, which leaves the entanglement intact, and forcing a particular outcome, which disrupts it. As quantum physicist Chad Orzel puts it, whenever we try to control the state of a quantum particle, we lose knowledge about the complete system state. The inherent randomness of quantum measurements prevents us from encoding a preferred outcome, effectively dashing hopes of faster-than-light communication. The dream of faster-than-light communication through quantum entanglement faces a significant hurdle. The quantum realm, it seems, is not easily tamed. It's a world where particles can be in two places at once, where the act of observation changes the observed, and where the rules of the game are fundamentally different. This quantum dilemma underscores the impossibility of using entanglement for communication, reinforcing the fact that in the quantum world, there are no shortcuts, even at the speed of light. The heart of the issue lies in the difference between making a measurement, which preserves entanglement, and forcing a specific outcome, which disrupts it. Let's unravel this a bit. You see, in the peculiar world of quantum mechanics, the act of making a measurement pertains to observing the state of a quantum particle. This observation doesn't disrupt the entanglement between particles. The invisible thread linking them remains intact. So while you can't control what state you'll find a particle in, you can still enjoy the spooky correlation between entangled particles. But what if you want to force a specific outcome? What if you want to encode a message in the state of a particle, hoping it will instantly appear in its entangled partner, no matter how far apart they are? Well, that's where you hit a quantum wall. The moment you try to force an entangled particle into a specific state, the entanglement vanishes. Poof! Just like that, the other particle is left unaffected, maintaining its random quantum state. The correlation, the very essence of entanglement, is severed. Chad Orzel, a quantum physicist, emphasizes this distinction. He points out that controlling the state of a quantum particle leads to a loss of knowledge about the full system state. The act of forcing an outcome disrupts the delicate balance of quantum mechanics. But why does this happen? It comes down to the inherent randomness of quantum measurements. You can't encode a preferred outcome because the universe doesn't play favorites. The quantum world is a game of chance, where every measurement is like a roll of cosmic dice, so the dream of instantaneous information transfer through quantum entanglement runs into a stark reality. The laws of physics don't allow us to force a particular outcome without breaking the entanglement. Quantum states can't be cloned or copied, and any attempt to read the state alters it irreversibly. This inherent randomness of quantum states ensures that faster-than-light communication remains a dream. As we dance to the rhythm of quantum mechanics, we must remember, in this grand cosmic casino, the house always wins. So where does this leave the prospect of faster-than-light communication, you might wonder? Well, the realm of quantum entanglement, as fascinating as it is, seems to slam the door on this tantalizing possibility. Let's revisit the key points we've discussed. quantum entanglement, this mysterious bond between particles, allows the state of one particle to instantaneously influence the state of its distant partner. This phenomenon, while defying our classical understanding, is well supported by experimental evidence. Yet, it's crucial to remember that this doesn't imply the possibility of transmitting information faster than light. The challenge lies in the fundamental difference between making a quantum measurement and forcing a specific outcome. While the former leaves the entanglement intact, the latter disrupts it. As quantum physicist Chad Orzel emphasized, controlling a particle's state results in a loss of knowledge about the full system state. The inherent randomness of quantum measurements forbids encoding a chosen outcome. So, the dream of faster-than-light communication through quantum entanglement stumbles upon this hurdle. The inability to force a specific outcome, to clone or copy quantum states, and the irreversible alteration of the state upon measurement, all conspire against this dream. These constraints, dictated by the laws of physics, serve as the final blow to any scheme of faster-than-light communication using quantum entanglement. But don't be disheartened. This conclusion has profound implications. It reinforces the fundamental limit on the speed of information transfer, upholding causality in our universe. It keeps us grounded in our understanding of the universe, reminding us that while quantum mechanics can be counterintuitive and mysterious, it doesn't break the fundamental rules of the cosmos. In the intricate dance of quantum mechanics, where randomness reigns, faster-than-light communication remains unattainable, preserving the causality in our universe. So even if it seems that God plays dice with the universe, at least we can rest assured that the dice can't roll faster than the speed of